Well, first of all, I'd like to say that I have handwritten transparencies because Yulia Tanizaki is my hero. And actually, it's because Zohar Kovayatsky once came in the 17 and gave a talk on his tablet, and I was so impressed. So I'm very disappointed that Zohar has gone to the dark side. But anyway. What I'm going to talk to you about is some work I did with Pisarski R in last June. It actually was based on thoughts we had like 10 years ago. And what's also interesting is that since our paper appeared, there were some lattice results that I think are very interesting. So the basic idea is that, can you turn this light off? Yes. Middle that we're talking. In an SUN gauge theory without dynamical quarks that we all know semi-classically, that you have integral topological charge, but there's a very good reason that I'll explain as to why we think you need fractional topological charge proportional to 1/n. How such configurations could arise was first pointed out by Hooft in 1980, and there's a lot of other work by Pierre van Baal and others. In particular, Mita Runzal, Eric Poppets, Lexi, I believe Larry, have done work on a femtose lab where this arises very naturally. And what we're going to suggest is how this might arise in the continuum. Okay, so I won't spend too much time on this. You all know that there are instantons classically, they're self-dual or anti-self-dual solutions. And the action is quantized in units of A pi squared over g squared times an integer. And we know all classical solutions and the like. Okay, so if the only important thing you need to remember is that since it's a classical solution, you have scale invariance, and so instantons come in all scale sizes. Rho that runs from 0 to infinity. Okay. What is less obvious is what happens when you compute at non-zero temperature. Now you can compute semi-classically because then the temperature is very high, the coupling is small. And what is less obvious, well, you can certainly tell how the partition function from the single instanton sector should fall. It's e to the minus a pi squared over g squared. G squared goes like 1 over a log. And so this is going to fall like 1 over a power of the temperature. This coefficient C is directly related to that of the beta function. There's a -4 because of the integration over scale size. You get d rho over rho to the 5th. So that's where it comes from. But for no flavors and 3 colors, this is 1 over t to the 7th, and it dies like a bomb. What's amazing is that the lattice, first of all, can pick out a signal for this. And they show that the temperature, this power law seems to hold out the temperatures of 300 MeV. And for those of you who are familiar with how badly perturbation theory works at non-zero temperature, which generally fails at hundreds of GeV, it's really quite astonishing. Now, the overall constant doesn't agree. It's about 10 times what you'd expect from the one loop result, where the one loop result includes powers of 1 over g squared from the collected coordinates and the like. But clearly you need a 2-loop computation. But the fact that this works down to this temperature is really, I think, quite astonishing. And one of the remarkable things amongst many that the lattice has told us from numerical simulations. And this was work done by Bersani and collaborators and my colleague Peter Petretsky.
When you say it works, you mean the power is right.
The power is right, not the, it's 10 times bigger than what you expect, but the power works. And they can really, they've measured this up to temperatures of, I think, several GeV. They use very clever numerical tricks, which I'm not competent to comment on. But still, it's 300. If they had told us it fails at 300 GeV, I could, Larry, you wouldn't be surprised, right? It's not. Fine, perturbation theory fails. What else is new? Or semi-classical. Why should semi-classical work with perturbative It's really astonishing. What's more susceptible? Yeah, I would have expected it to fail to work less well than perturbation theory. Okay, you can also compute the topological susceptibility. You add a term proportional to theta times q, and you measure the value of q squared basically. And what you find, this is work done by Claudio Bonatti, Massimo Delia et al. From 2013, is that at least in the limit of large n, so this is pure gauge, large n, there's, first of all, a weak dependence on n, and I'll show this later, that the susceptibility appears to be constant in the confined phase and non-zero, it's of order 1. It appears to be very small in the deconfined phase, and so dominated by instantons there. And there, it's a first order transition, so this is going to drop. There's evidence from that from the lattice from 3 colors. And it's not clear, but it looks like there's some transition region whose width is on the order of 1 over n. Of course, they can't calculate exactly at large n. They calculate it n equals 3, 4, 6, something like that. And so the question is, what generates the topological susceptibility in the confined phase? It's certainly not instantons. Why? Well, okay, let me go on and review what happens with quarks. Well, here, as I said, for temperatures bigger than 300 MeV, it appears to be dominated by instantons. There's an intermediate region between the chiral temperature at T chiral, which is about 155 and 300, where it's not instantons, it's a slower fall off. This is the 4th root of the topological susceptibility. So this is the 155. This is something like 300-400. So it's instanton dominated here. It's something else here. It's not clear what that is. And below the chiral temperature, it's approximately constant.
Sorry, for these experiments, you have quarks?
Yes, yes. And this is 2 + 1 flavors. Yes.
And the
Yes, this is with quark.
And the 2 different bands or 2 different calculations disagreeing that much?
Yeah, I think, well, Peter would certainly tell me his is better. But there are recent results with dynamical quarks that are better, and I probably should have included that. It was just, this is the one curve where you clearly differentiate between this region where it's instanton dominated and where it's chirally symmetric, but something else. That was my purpose in showing that.
So the value of some gas goes to the lower curve, but not the one above.
This is the dilute instanton gas.
Okay, so the other calculation doesn't agree.
They
with it.
didn't agree, but they've done that. And there's a lot of work done in particular related to axion production in the early universe. And so there's a lot of groups doing this, Guy Moore and others. And
Is it obvious that the other one doesn't agree because it's a power law? It doesn't really, you said that the coefficient is not fixed, so the power law is different in the gray data?
yes. Well, this is the claim they make. This is the claim they make.
I
But
mean,
if
in
you
this
would
mean small temperature region, I meant the gray band.
I think you should ignore that. I'll erase it when I give this talk again. This is almost 7 years old, so. The point is, it's dominated by instantons. That's what I find amazing.
And there, the actual coefficient in front is being
No,
calculated correctly, and that's part of the comparison.
right, absolutely. And that, as I said, is 10 times too small. But that's, nobody's computed the 2-loop instanton.
But 10 times too small here, where it's the topological susceptibility.
It's the overall scale. When I say it agrees, I mean the power law fall off agrees. That's all. Okay. So why is there a problem at large n? Well, we know that we hold g squared n fixed as n goes to infinity. So any instanton contribution is going to go like e to the minus n. However, Veneziano and Witten argued some time ago that the susceptibility should be of order 1 in SUN as n goes to infinity, at least in the confined phase. Okay, this is a slide in case anybody asked me about couldn't you have some sort of liquid of instantons? I don't want to go through the details. The point is the action is going to be proportional to n. You can easily see that at large n, what's going to dominate is a single coupling constant, or if you wish, a single scale size. But in order to get something non-zero, you're going to have this action vanish. And I don't see how that could happen naturally. But it is theoretically possible. Okay. A much more natural thing is if you have things with fractional topological charge. Now, at the outset, let me say, I'm not claiming that if you have a box with periodic boundary conditions that you will be able to measure fractional topological charge. The question is whether or not the fluctuations are characterized by those with integral topological charge or fraction. In particular, as pointed out by Huff, Pierre Lamballe, Sedlacek in the early 80s, you can have Z and twisted boundary conditions where fractional topological charge just pops out. And however, they're manifestly finite volume because you have to have these twisted boundary conditions. And so the question is, do they persist in infinite volumes? Okay, well, in this sense, the work by on a femto slab is really very pretty. There's an excellent review by Eric Poppins. What happens is if you go to a femto slab, you can make the size of the slab very small so that the you can use recoupling results, and at large distances, you have effective theory in 2 + 1 dimensions. And by the usual Polyakov mechanism, you can show that you have some sort of confining monopole instantons with topological charge 1/n. The size of the monopole instantons is on the width of the femto slab. So the problem is you don't know what happens as that slab becomes larger and larger.
Sorry, what's this slab mean?
You take, say, the Z direction and you make it 10⁻⁸ Faraday. So your coupling associated with that small dimension is very small, and you can use semi-classical techniques reliably.
I'm saying that for the physics system, what is the justification for existence of the?
Because you can calculate analytically, and I think if you can go to a limit where you can calculate analytically without apology, you should. It's always worth doing so. No, for example, Yuya and Mitat have computed on a torus where 2 of the dimensions are small. So it's a femto torus and the like. Well, you may not, I mean, you don't know what happens. The question then becomes what happens when this becomes big, but at least it's a clean limit.
Yeah, got it. Small comment. I mean, you could ask the same thing about Lagrange. Why go to Lagrange?
Yeah.
The real world is that's equals 3. That's it.
So over there, I can think like 1 or 3 stories on the line.
But it may or may not be small. You don't know. But it gives you some way of calculating something.
Yeah. But yeah, then I can say that the limit the calculus was finite. But the real thing, I don't know whether.
Well, that's what I'm going to talk about. That's what I'm going to talk about. But I see Larry's in the back now, and so he's probably going to ask, what about the real world? So, okay, I'll get to that. Okay. Okay, so the punchline that I'm going to say is the size of the monopole gets stuck on the order of the confinement scale. The dominant configurations have one size. And okay, our arguments are kind of hand wavy, but I'm going to show you a way of that this can be tested on the lattice with present day techniques. It's not simple, but it's doable. So it's basically saying everything that Mitat and Eric and Unburn. Were you involved in this too?
Possibly, depending on which aspect.
Yeah, it's just they get stuck at the lattice at the confinement scale, but their quality. So in answer to your question, their qualitative conclusions remain valid.
But this is really constrains their size only in one direction. What about the other direction? They might.
No, I'm arguing what's happening. I'm just saying as a hand wave. No, and I'll. Okay, so. Okay, I could go on. Okay, I have this stuff about the ZN model. I don't want to discuss it at too much length because it gets kind of technical. And well, I could go back. So in it, CPN -1 model in 1 + 1 dimensions, you have one dimensionless coupling constant. The global symmetry is SUN mod ZN. These are complex value vectors who have unit norm. And this is an old story, so I don't want to, it's asymptotically free. Witten and Dada, Lusher, and DeVecchia solved it long ago. You can calculate every single instant time you want to. Their analogy of being self-dual is this. And so you have some configuration, this ZI, that depends upon some vector, and you have some scale size. This is scale invariant. Okay, everything goes through. You can compute the one-loop fluctuations about any instant time, and it appears to be exponentially suppressed. Now, this depends, the moduli space for large n gets complicated. But you can calculate directly at large n and show the susceptibility is, because of this model, the number of degrees of freedom, it's not 1, it's 1 over n, but it's not exponentially suppressed. So we have a solution for the kind of configurations that can contribute are, instead of taking something that's single valued, because the true manifold space is SUN mod ZN, we take something that when you go around by 2 pi, you pick up a factor of e to the 2 pi I over n. And when you do that, instead of getting, this is some fictitious vector potential, you get topological charge that's fractionally, that's 1 over n instead of n over. And the point is, to obtain this, you have to have multi-valued solutions. And that's the only thing I want you to remember from this model. The other thing is that when you do this, you're manifestly looking for a solution out of the classical field equations, but the effective field equations once you integrate out the z's. And once you do this, you have dimensional transmutation, you have a mass scale that's generated dynamically. And so the size of these instantons is naturally going to be 1 over the dynamically generated mass that is on the order of confinement distance. So this is the lesson I want you to remember from the CPN model. The details you can forget about.
Sorry, can I just check? They're really fractional. Even the gauge invariant data is fractional. Is that right? It's really
well. If you calculate, well, it's kind of trivial. You see this. You take a phi and you take integral a phi d phi, and you're going to get, because there's a 1 over n. You get 1 over n.
okay, but just to understand, the gauge invariant data is
single value. Yes. Yes. You mean is that from your new thing?
Yeah. Yeah.
Yes.
Or whatever the right thing is.
Yes. And for the z.
And for the Z.
Right. Yeah. No, that has to be true. We're just kidding. I'm sorry.
You said you need to integrate stuff out to find these solutions. It's not as you don't get solutions to the classical equation in the form you want. Is that right?
You probably, we looked at solutions of this. That's what we did. So, could you get that from me? Probably. We didn't look at that. And we didn't look at explicit solutions because, in fact, it turns out that the quantities of interest for the lattice, I wouldn't compute the topological susceptibility using these configurations, because you have to find a stationary point of this, and it's a non-local equation. I'm just using it as an illustration. Okay, let me go on and tell you what happens in a gauge theory. And so one way of characterizing topologically non-trivial solutions, not to look for a solution, but just to show how things are quantized, is you parameterize between one gauge transformation, one gauge potential, and some non-trivial gauge transformation of that. And then by the usual argument, you can compute and show the topological charge is related to the Chern-Simons form of the gauge transformation at spatial infinity, and that's an integer. Okay, that doesn't get the action right, but it tells you it gets the topological charge right. What you need to do is, if you want to get fractional topological charge, first of all, you have to put in the Zn symmetry somewhere. So that's what this matrix does. And then the instantons are basically SU2-ish, so you need to combine this Zn symmetry and the SU2-ish nature of the instanton. I'm not going to go through these details, but that's the basic thing that you need to do. So you need to take some kind of transformation that mixes the two in a non-trivial manner. Okay, and then you compute the topological charge. We have some parameter related to the gauge transformation. We work in A naught equals 0 gauge, but then this funny parameter looks like an A naught field. Anyway, you can compute. And as actually Larry showed in an appendix of our RMP, it's related to the magnetic charge at spatial infinity when you do it in this way. But again, you take the typical kind of magnetic charge you get, and you get topological charge 1. So who the F cares? Well, the point is this is a pure gauge theory. So we can take this magnetic charge and we can pull it apart into two parts where there's a Z2 flux tube connecting them. By a Z2 flux tube, I mean if you take a Wilson loop in the fundamental representation and go around, you get a factor of e to the I pop. Since gluons live in the adjoint representation, that doesn't matter. But when you do that, you then see that each of these pieces, since it's just the previous integral involved the magnetic charge, is going to give you a half. So, as I emphasized originally, to observe each of these separately, in between, you're going to have a Z2 twisted boundary conditions. Okay, well, this is a picture. And the for SUN, what you then have is a lot of Zn monopoles, and they'd be connected by some sort of flux tube and give you unit topological charge. In this, we also depend upon work of Unsal, who showed on the Fentos lab that you get what you'd expect, that theta dependence is theta over n and not f of theta. But I don't want to go into that because of reasons of time. I want to show you a different configuration that's somewhat more perhaps intuitive. Consider working in the deconfined phase and take a constant, what looks like constant, what is constant telonomy, constant A naught. And I'll choose these factors, and this is some matrix that's related to a Zn matrix. And if I compute the thermal Wilson line, the thermal Wilson line, I get an element of Zn. Okay, fine, I can do that. I can calculate the value of this holonomous potential, and I'm just going to get something that tells me that unless it's this thing is an integer, that I'm going to get something non-trivial over space-time. Fine. And then I had a Zn monopole. So this is the usual Dirac monopole where I add a factor of 1 over n. So you have, it's one thing on top in the upper hemisphere of space, it's another thing on the bottom, and they agree by gauge transformation at the equator, and that gauge transformation tells you that it's a different element of Zn, and this tells you it's a Zn magnetic monopole. And you can argue then, calculate that as A naught goes to infinity, you have this constant, and then you have a 1 over R fall off, etc. Okay, and then you compute the topological charge, and what you find is you get this expression. And basically, if these two matrices are equal, you get n minus 1 over n. If they're not equal, you get 1 over n. And this is basically similar to what Hoof did in a Zn in a box with Zn twisted boundary conditions, but we're now putting the boundary conditions at infinity. Okay, well, these are one form of fractional topological charge. I'm sure many of you know an alternate solution by Kron, Van Baal, Lee, and Liu from 1998. The difference between the configurations is that for them, the magnetic charge is an integer, and they have a dion where basically what happens is for this Q, instead of being at a minimum where this is an integer, it's half integer. So it's not the minimum of the potential, it's the maximum. We take a holonomous potential where it is.
Rob, I'm sorry, what was Q versus K? it was K in the Wilson.
Q is just a parameter here that goes from 0 to 1. K is an integer. It's this matrix. I'm sorry, it's this matrix. Yeah, I'm going kind of fast.
Yeah.
But I mean, if K is an integer.
No, K is that matrix. I misspoke. K is that matrix.
Oh, and Q is multiplying that matrix.
Q is multiplying that matrix. I misspoke. I apologize.
So Q is just a number.
So are you, what are you assuming here? Are you assuming that what is the trace of the holonomy is doing what?
It's just a configuration.
Did you
It's
put it
just
in
a test configuration.
And then Q is determined dynamically by minimizing the function.
Yeah. My only point is that we're taking a configuration where you're at the minimum. They took something where they're at the maximum.
They being
Kralv and Bao, Li, and Liu. And it's why it always bothered me for years.
But if the holonomy goes to an element of the center at large distance, the configuration is smooth, then the topological charge is an integer.
Not if you take a ZN manifold.
But then you're messing with what the
Boundary
holonomy does
conditions at
to
infinity.
a large distance.
Yes, yes.
Right.
And it's actually in our paper if you look at it. Okay, well, yeah, okay, so there are these differences and, okay. My point here is that it's different from Kron van Baldi and Liu. Let me go on, okay, that I should have deleted. These are configurations in which you have non-zero holonomy and magnetic charge, but we know that the magnetic charge is confined in the region where electric charge is deconfined. So they may be relevant for some region in temperature, but eventually instantons are going to dominate. So it's just a test configuration. In the confined phase, these are dions. They have constant holonomy. And clearly, as the temperature goes down, they're not going to propagate space just straight up in time. They're going to be some kind of vortices tangled on the order of lambda QCD. Okay, the question is, what configurations dominate, 1 over n or 1? In this, there's an old suggestion by Robert Edwards, Urs Heller, and Rajamani Narayan, in that in the pure gauge theory, to measure a fractional topological charge, you could do this by using a chiral symmetric quark propagator, that is the overlap, not in the adjoint, but the fundamental representation. And the reason is that the fundamental, you have 0 modes for each chirality for integral topological charge. If you want to measure something with fractional topological charge, you'd have to use propagator in the adjoint. And this, they claim to have evidence of that, but this was a long time ago.
Sorry, I'm missing it. Why is it easier to use that?
It's not easier, it's necessary. All you're going to see with an operator in the fundamental representation are 0 modes associated with integral topological charge. But this is a pure gauge theory, and for the adjoint representation, d mu g mu 5 picks up an extra factor of n.
And here, are you using overlap operator for Majorana adjoint experiment?
Presumably direct. You could do it for either. You could do it for. That's what they do.
Maybe extra factor 2 is there.
Well, that's associated with left and right. So
Yeah,
you could do it for.
Okay.
Are you saying that the fundamental direct operator doesn't have any 0 modes in a fractional system?
It won't even exist.
It's not true. I mean, I have a paper with Meetup and Thomas Schrader discussing this stuff. But anyway,
Okay, then perhaps I'm misstating it, but
why is that? I mean, he has the fractional configuration. Is it not true here?
I think you need to use extra flavor or area number.
yeah, I'm not, this is pure gauge. I don't have dynamic
Yeah,
force.
that's a color ice boundary condition. Okay, I'll do my demo.
No, but look, if I have a Z monopole, or say take a vortex, okay? So in the fundamental representation, I get e to the 2 pi I over n. How can you have that with an instant time? Okay. Okay, well, let me, for reasons of time, I'll probably just conclude with this. In fact, I think there's very interesting evidence for fractional topological charge from work done by Claudio Bonanni, and Massimo Delia, who are extremely serious lattice people. So they looked at SUN for 3, 4, and 6 without quarks. They did something called parallel tempering. The point is, this is what their Q looks like, this function of Monte Carlo time. And it oscillates all over the place. Then they do cooling and bang, it falls into integers. But this agrees with our analysis that, if you measure something in a periodic box, you have to get integral topological charge. The question is, what are the fluctuations? Well, they measure this, for example, the topological susceptibility versus n, and that ratio versus the string tension square. This is 1 over n. They looked at 3, 4, and 6 colors, and that's a beautiful straight line. You look at this coefficient, it's small. Large n limit appears to be very smooth as n goes to infinity, because it's pure gauge. It's what we all expect. If they look at the kurtosis, so this is the moment of the 4th power of the topological charge. I won't go through the argument for a dilute gas of integral charged objects. This quantity would be minus 1/12. This is what they get on the lattice. So if it's integrally charged, it would be flat. That certainly doesn't look flat. If you have a dilute gas of fractionally charged objects, you get minus 1/12 times 1 over n squared. That doesn't work well from their data. What they find is a value that's more than twice as large, but that certainly looks like 1 over n squared. In fact, they find a good fit. If they allow the power to vary, it's about 2.1, I think. But to me, they don't stress this in the paper. I think it's strong evidence for a dense system of objects with fractional topological charge. So, and we had long discussions with this, and I don't know why they weren't jumping up and down. I heard each of the authors speak on this once, and it was only when I heard it the 3rd time that I got it. So I think it's very interesting, but I think really the crucial test would be to measure with an adjoint operator using a chirally symmetric overlap, and that's hard. It's just hard. It's the adjoint. It's just a hard business.
So in the previous slide, you showed that you get this integer
Yes.
cool, right? But you're saying now when you look at the kurtosis, it's more differential. You're seeing signs of fractional charge.
Well, the previous slide, as I said, if you cool the system with periodic boundary conditions, I certainly agree you're going to find integral topological charge, and that's what they find.
Question is whether there's some sense in which those integer charge configurations can be viewed as
Right, and so that's
substructure.
right, and that's what the kurtosis claim reveals.
And they don't claim. I don't
Okay, so
but they're very serious people. They really work hard. There's parallel tempering, I think maybe Derek.
So Rob, let me ask what seems like a bottom line question to me. If you say that a typical contributing configuration has some sort of lumps of topological charge 1 over n, which gives a beautiful picture, but you say it's dense.
Right. How do you?
Right there, I don't know what it means anymore.
No, fair enough.
I
But
don't know what the
yeah,
substance
but
is.
if you look at the 0 modes, then you can determine not just the position of the 0 mode, but you can look at its eigenvector and determine the size.
Well, but a
So
typical configuration is, you're gonna say has lots of lumps, lots of anti-lumps, and all those 0 modes will be lifted because things are close together.
right. But you'll certainly be able to distinguish between something where things are, you have n of them close together and where n are spread apart.
So we're saying in some sense, we're right on the edge of distinguishability.
But it depends what the eigenvector is.
I mean,
It
is there
depends.
another observable they could look at, which was,
Well, yeah, in particular, distinguishing between Kral, Van Baal, Liu, calorons. One could distinguish between, one could measure the Z3 charge and the Polyakov loop locally. That's easier.
So how do the size of these objects compare with the lattice space?
Yeah, they're coarse lattices. They're coarse lattices. I mean, to really demonstrate this, even in the pure gauge theory, you're obviously going to have to go to very fine lattices, right? Or nobody's going to believe you. You're going to need very fine lattices. So it's not a simple task. I'm just saying this evidence of the kurtosis is very suggestive.
okay. I didn't understand the part between 0.08 and 0.09. So
Well, what they say in the paper is that this is the value they get, so it has nothing to do with fractional charge. And to me, it's just like, okay, it's not a dilute gas, but it's some sort of, look, you can certainly tell the difference between 1 over n squared and constant, and it's not constant. But your point, Larry, that it's clearly going to be some sort of complicated thing is certainly valid. Okay, so given time, let me just then, okay, the question is what happens with dynamical quarks? As I said, with dynamical quarks, if you have a Z3 flux line, you go around, you pick up a factor of either the 2 pi I over n. So your natural guess would be, and then I'm just going to flash this. This is work by Lineweber and collaborators. They look at the difference between Zn vortices. Remember, I was talking about dions, but they did vortices in pure gauge versus dynamical quarks. And I just want to flash this picture, and then I'll be done. This is work that appeared, well, there's more recent work last year. This was from a conference proceeding. This is the density of free vortices in pure gauge. Now it's gauge dependent. You may think it's kind of hinky. That's possible. But as the number of vortices increases, the number of, as the mass of the quarks goes down, the density of vortices increases. And it would, it's just exactly the opposite direction. You would have thought that the quarks would have pushed out the vortices. It's not what happens. And this is a graph of the connectivity. I don't want to explain it. This is pure gauge. This is 2+1 flavors. This is really like near QCD. And just looking at it, you can see, geez, there's more vortices going on here than there. And I don't understand that at all. It's just astonishing. Okay, let me just finally conclude with, I argue there are 3 regions at non-zero temperature. I think what's very interesting is to consider what happens at low temperature and non-zero density. And on the basis of analogy to a non-zero temperature, we argue that, in fact, the perturbative regime where instanton dominates is mu quark of 2 JeV. You'll never reach this in a neutron star. In fact, calculations by Korkolev, Rorinen, and the heroic Finnish group dominate that mu quark of 1 JeV is perturbative. So there's going to be an intermediate region relevant for neutron stars where it's dominated by Zn dions and massless quarks. And with that, I won't go into the details, except to notice that nobody ever did the exact calculation for the one loop calculation of the instanton at 0 temperature, non-zero density. It's still remaining to be done.
Yeah, it's so.
So on that, what's the line miles to go before I sleep? So with that, I thank you.
Let's have questions.
So about the density of vortices, so how should we understand it? Because adding quark beta function becomes smaller, so naively confining forces becomes weaker, but with more dense vortices, it seems to be opposite. So
I have no idea. I really don't understand. Now, as I said, it's a gauge dependent way that, and I believe what your colleague in math at Durham with Swansea has a gauge invariant way, depending upon persistent topology.
So I have to say, I haven't got, I'm not an expert, so I don't know, but from dealing with him, they have some way of doing it that he said better, it's less gauge dependent. It involves using persistent topology to find patterns in the numerical data.
Yeah.
I don't know the details.
Yeah, because just the, I mean, what they do is they plot each element. You know, and they diagonalize it and they look where the phase lies. And then they characterize them as, you know, near here, near there, and by imposing a gauge fixing term. But it makes you nervous that it's gauge fixed. So I'm not, that's a significant worry. However, it's hard to imagine that gauge fixing is going to mess up the density. I mean, you might ask, do the absolute numbers, are those, they're manifestly gauge dependent. But the fact that the density goes up is just, that's amazing. And you know, it's Derek, so he always has beautiful pictures.
Good questions. I guess not.